This final chapter, Chapter 4, examines first the factor sensitivities of swaps and explores later how traders might use swaps to take views on market direction. We restrict the discussion to interest rate swaps due to time constraints. We examine first the sensitivities of an interest rate swap to parallel movements in the yield curve and then to a steepening or flattening in its shape. Then we show how swaps can be used to take a view on an expected change in interest rates. More advanced trading strategies involving swaps will be analyzed in later modules. Worksheet sensitivities calculates in cell K20 the present value of the swap from the perspective of the party receiving fixed, whom we will call the receiver for short for the rest of this chapter. And those calculations will be based on some defined LIBOR curve as we simulate changes from the original curve appearing in column F to some new curve appearing in column G. Right now, of course, the numbers in column F and column G are identical. Note, for the first time in this module, that we have slightly altered the LIBOR curve a little to make it completely straight. This will make our life a little easier in a few moments when we come to defining pivots in the shape of the curve and simulating those pivots. Cell H23 plays a critical role in the spreadsheet and allows you to input a parallel movement upward in the yield curve by any amount you designate. You would need to input a negative number if you wish to simulate a downward parallel movement. Note finally, before we start working with this worksheet, that the changes referred to earlier in the initial few values of LIBOR in the curve in column F have caused the 3-year swap rate to increase from our old 5.23% established previously in this module to 5.34%, essentially on account of the increase in the first few values in column F. The revaluation of the swap occurs automatically as soon as you input any number you desire in this cell H22 and will appear in cell K20. Thus, for example, a 5 basis point parallel increase in rates gives rise to a loss for the receiver of $139,323, while a 20 basis point parallel drop in rates results in a gain for the receiver of $559,508. There is a graph appearing immediately to the right of this pricing table, which allows you to see the yield curve movement that you input in cell H23. It is not possible for us, due to scarcity of space, to show both the graph and the table at the same time, but obviously you can do so much more easily by opening in full the spreadsheet in your copy attached to this module. Nonetheless, if, for example, we change the entry in H23 from minus 0.20 to minus 2% and hit enter, you will notice how significantly the graph has shifted from its previous position, which looked like this. Continuing with movements in the curve, cell H24 gives you the ability to make the curve pivot off its midpoint. Let's return cell H23 to value 0 and deal with cell H24. Curves, of course, never behave nearly so elegantly, but to make easier our programming work in Excel, we will define a 100 basis point pivot as meaning, and please keep your eye now on the new curve in column G, that the gap in rates between the first and last LIBOR values in column G increases by 100 basis points, while the curve continues to be completely straight. This gap right now, as you can see, goes from 4% to 675 and therefore adds up to 275 basis points, and the 100 basis point pivot we are about to simulate would take it up to 375 basis points by pulling down the first few values of LIBOR and pulling up the last few values of LIBOR, exactly as has appeared now in cell G5 to G16. Note there has been a 50 basis point drop in the first value of LIBOR and a 50 basis point increase in the final value of LIBOR, in total representing therefore a 100 basis point steepening or pivot in exactly the way we defined that term pivot, by reference to the midpoint and not any other point in the curve. By the same token, if we want to simulate a negative 50 basis point pivot, which would therefore represent the curve flattening to some degree, we would insert minus 0.5% in cell H24 and watch the curve becoming less steep than it was before. Finally, you should recognize that this worksheet enables you to simulate or combine parallel shifts with pivots if you so wish. As one final visual aid, we have reproduced the pricing table a second time underneath the table you saw before, but starting on row 30 this time, along with the graph immediately to its right. But this time, the graph comes with two scroll bars underneath it, which enable you to simply click and drag left and right to simulate either the curve shifts using the top scroll bar or the pivots using the bottom scroll bar, or obviously both, to engage in the simulations that you want. As you do this, you will find both the entries in cells H49 and H50 changing, and those are the cells that were previously the input cells for shift and pivot, as well as all the numbers in the relevant parts of the table, which will change as well, and most importantly in cell K46. And those will move up and down in exactly the same way as they previously did in the first part of this worksheet, reflecting the impact on the value of the swap of the shifts and pivots. But please note, as you play with this worksheet, that here in the second half you can only simulate changes to the shape of the curve and pivots by means of these two scroll bars, and categorically not by inputting those changes directly in these two cells. That's why we have colored them in purple and added the legend at the bottom in bold: do not modify. We now simulate a 1 basis point decrease in rates and find that the receiver has a gain of $27,891 relative to a notional, we remind you, of 100 million. This sensitivity of the swap to a 1 basis point shift in rates is often referred to as the dollar value of 1 basis point, or DV01 for short. It is one of the most fundamental risk management concepts in all of fixed income. We should here point out that there is in fact a very small inaccuracy in the way the worksheet has been designed, but that we have tolerated it to avoid complicating the exercise too much. Specifically, when the curve shifts, the discount factors will all change, as can be seen in the worksheet. But the first LIBOR setting under the swap itself would not change, seeing that it was locked in already at 4%. Therefore, in reality, the payment in question for that first period would not change either, but its present value would change given the change in the related discount factor. The impact of this correction would be relatively small, but should not be ignored in real life, especially if the curve moves by substantial amounts as opposed to just 1 basis point. Generally, you should not be too surprised that the receiver has a gain, since the fixed cash flows he is receiving are now being discounted at lower discount rates. It follows that receiving fixed under a swap is one way of taking a view on declining interest rates. It is useful here to remember our discussion from Chapter 2, in which we decomposed an interest rate swap into two bond positions, one long and the other short. In the present case, the receiver can be viewed as owning a fixed-rate bond which it has funded with a LIBOR-based liability. The fixed-rate bond would of course rise in value when rates fall, while the floating-rate liability would essentially remain as it was, since floating-rate assets or liabilities have little price sensitivity to changes in interest rates, as their coupons follow rates up and down. Thus, the price effect on the receiver of a 1 basis point drop in rates should be roughly equal to the price gain of owning a 3-year, $100 million quarterly pay bond whose coupon is 5.34%. In general, it can be shown that the DV01, or dollar value of 1 basis point, of a swap is very nearly the same as the DV01 of a fixed-rate bond, whose principal, coupon, maturity, and day count/frequency match those of the fixed leg of the interest rate swap. Worksheet DV01, which you see here, shows in cell E13 this bond's price when rates are 5.34% and therefore equal to the bond's coupon. It is no surprise, therefore, that the bond initially is trading at par. Cell E15 shows the new price when rates have dropped to 5.33%, which you can see here in the formula as the original discount rate in cell C7 minus 1 basis point programmed into the PV operator. It confirms that the gain in value of the bond is $27,555, pretty much the same gain as we calculated under the swap. The difference is due partly to the rounding of the swap rate to exactly 5.34%, as we have done in this spreadsheet for the bond, and also to the small inaccuracy in the swap worksheet regarding the first cash flow, which we discussed just a minute ago. Returning to worksheet sensitivities, we presumably would expect a loss for the receiver if rates increased by 1 basis point. Simulating a 1 basis point increase in rates in cell H23 reveals indeed a loss to the receiver of $27,882. You may have wondered whether this $9 difference in the absolute magnitude of the loss versus the gain we calculated when rates went down 1 basis point is significant? The answer is that here it is quite trivial, obviously, but that it becomes far more pronounced for larger movements in interest rates. To confirm this, you are asked to verify that if rates rise or fall by 100 basis points instead of just 1 basis point, the gain and loss for the receiver would become 2.833 million in the case of a drop in rates versus 2.745 million when rates increase. Click the pause button while you perform this exercise. Assuming you are able to confirm the results we had mentioned, you might also have recognized the similarity to another fixed-rate bond phenomenon known as convexity, which refers precisely to the nonlinearity in the P&L graph of a swap when rates move up and down. Again, if you know enough about bonds to know that a fixed-rate bond price-yield graph has a convex shape, the fact that a swap has the same property should not surprise you any longer. The blue graph you see here plots the P&L for the receiver against parallel shifts in the LIBOR curve. We have added a straight line in red to the graph so that the curvature in the blue curve can be seen more easily. The DV01, sometimes also referred to as the duration, is best understood as the steepness of the graph, while convexity is best understood as the curvature of that graph. Both concepts are discussed extensively in several of our other modules. Our next question is whether a pivot in the curve of 100 basis points, say, would also have an impact on the swap's value, and if so, whether it would be comparable in magnitude to the impact of a parallel shift. Resetting cell H23 to 0, but inserting 1% in cell H24 reveals a gain for the receiver, but in an amount equal only to $40,817. A negative 1% pivot would generate a loss to the receiver of $39,995. So there is a price impact, but a far, far smaller one than for a parallel shift of comparable magnitude. Note that by defining the pivot the way we have done, we have ensured that the arithmetical average of the LIBOR values appearing in column G after the pivot remains the same as it was prior to the pivot. In a sense, we have ruled out any price movements in the value of the swap due to an absolute increase in the average or an absolute decrease in the average and are really focusing on how the steepness of the curve as it increases or reduces causes the value of the swap to change. You should please try to remember these various results we have been illustrating when you study our more advanced module on especially what is called a constant maturity swap, where you will see a very interesting difference between the price sensitivity of the constant maturity swap and that of the regular interest rate swap that we have been analyzing here. We conclude this chapter by asking you to intuit a rough estimate of the receiver's P&L if the LIBOR curve pivots by 100 basis points again, but this time off the first value in column F rather than off the middle. To be more specific, we mean a scenario in which the rate in cell F5 remains unchanged at 4%, while all other rates increase such that cell F16 goes from 675 to 775, 100 basis points higher, and the rest of the curve in column G continues to be completely straight. Click pause while you think about this, and the solution will be provided as soon as you click the play button again. The intuitive approach is to recognize that the rate movement we asked you to consider can be simulated in 2 steps, which you have already experimented with. The curve first pivots off its middle by a total of 100 basis points, and then rises in a parallel manner by 50 basis points. You can see that we have correctly simulated the shift in the curve we had previously described orally, with the 4% at the beginning remaining 4%, the 675 at the end becoming 775, and all numbers along column G lying in a straight line. Fortunately, you cannot see the result in cell K20, but you should be able to estimate it more or less, because we know that the first effect, i.e. that of the pivot, should generate a minor gain for the receiver, perhaps again in the order of around $40,000 as before, while the second effect, the increase of 50 basis points in a parallel shift of the curve, would generate a major loss for him, perhaps equal to around half the loss we had calculated before, since the curve is moving up only half as much as before, and so somewhere around 1.4 million loss instead of what was previously a 2.8 million loss. Worksheet combined, which we will now click on, has the solution in it already appearing and confirms a aggregate loss in cell L20 of this worksheet of about 1.34 million, very nearly the result we had anticipated through our intuition. This concludes the lecture part of this module on interest rate and cross-currency swaps, and leads us to the 8 quiz questions of Chapter 5.